afternoon. Everyone in the world. Anyway, so, okay. Herane, okay, last day we discussed the equilibrium. So another one case I'll introduce about this equilibrium, that's limiting equilibrium. Right? That is the last movement of the equilibrium. So now we can consider is just to move, right? But that is the maximum. That's a possible place or that's a possible situation of the equilibrium. It's just one. The one point is to change. That equilibrium is broken, right? It is a case like this. You consider, let's say, a body is placed on a horizontal table, right? So table placed. Now it's in equilibrium, right? If I draw the body, let's say edge of the table, right, similar to this. So like you can see here, right? The weight of the body, the top down on the center of gravity, its weight, and then the normal reaction on this body acted in all the points like this, all the points there. The resultant of this all, because equally they acted on it, the resultant of this all we mark at this point normal reaction R. The normal reaction will not proportional or is not depend on the area, surface area of infected. So here also when it is at equilibrium and here the R equals mg, that's why it's being equilibrium. Here the weight is acted on center of gravity. There. Now there is no any reaction acting on this part. That part is out of, there are no contact. So it implies you that then forces acting on this side should be much greater than the other side. This side has smaller one. This side has a larger force. So then the resultant of the all the forces acting on this side, reaction force acting the left side, that should be greater than this. As they are resultant, same as the previous. And this way it is acted on the center of gravity. If it is not acting on the center of gravity, the moment it cannot be in. Also the R equals mg, but the resultant, the process on the right side, it's much smaller than the left side. Affecting in a reaction process very big. Effect the totally bigger. Sorry, effect the very should come. So this side is smaller, this side will be larger. So then the resultant come towards the larger. So that side it's acting on the same as the center of gravity as previous. Now let's see, if I take this body half of its length is out. The uniform radius is considered. Right is half. Now, weight acting on this body at the edge of the table. Our reaction, total, our reaction should be acted on the side also. In this case, that the right side, there are no any point contact with the table. The left side is only the contact with the table, but you can assume that the left side is not contact with the table. The only the contact point to the table is the center of gravity. That side is two forces acted. Same point here. Now the this block is in contact with this table only at this point only. That is passing through the center of gravity of the body. මේ වෙලාවේ මෙතන විතරයි යන්නේ. මේත් නෑ මෙහෙත් නෑ. normal force එක නැහැ. කෙලින්ම full force එක මෙතන. That's also in equilibrium now, right? That's R equals mg, and the body is in equilibrium. Yes, we see all three cases, the body is in equilibrium. If further you take it out, then like that, you can't bear. But really big, leave it. Because the normal reaction try to acting on this point, weight is somewhere, right? So object cannot be in equilibrium there, so it will happen because of the moment acting on these three cases. The moment is also zero. If it's point, so it will be normal. I call it a roll down. But this is the maximum case. That's maximum length which object can take out. This is let's say length and the start length is L. Right. This also this side. So this case is called the limiting equilibrium. This is the maximum. Further you take it out, what happens because of the moment given by the weight, the body will be brought down. Okay. So මේව එළියට ගන්න වෙන්නේ normal reaction එක මේක මත act වෙන normal reaction එක left side right side එකේ තියෙන normal reaction එක it increases, and at the point the normal reaction will act at only one point, that is at the edge of the table. So then this is a limiting case. Further you take it out due to the weight, the moment given by the weight, so it's rolled down. Okay, in this kind of cases we can consider as the limiting equilibrium. That is the maximum situation or value of the body's length can take out from the edge to be in equilibrium. Right, so then equilibrium, limiting equilibrium we can define like this: when a body is on the point of motion but is not moving due to a frictional force, because that due to frictional force yes, there any tendency to move on the side due to frictional force will not be changed. So this is only one example of this limiting equilibrium. You can make, because that some cases there's friction also, they resist the break the equilibrium. The friction is there, until friction is caused down, we can make it in a okay. You must write the topic as the limiting equilibrium. Okay. Right, and then limiting here means that an object is just that an object is that an object is just just on the threshold of motion on the threshold of motion or or sort of the slight force to now the slight application of force will result slight application of force will result in the motion of the body result in the motion of the body. You can draw this diagram one by one below the second one below this because I can write something in front of you. Right? You can draw this for like, first we write there the consider a uniform block is placed on the horizontal table as shown. Consider a uniform block placed on a horizontal table based on a horizontal as shown below. Okay, as shown below. Then you can draw this four figures one by one. It's better you can draw it one below another. First one and then second below it and third. I can write. If not, you can write in this way also. I can write in the bottom. Yeah, and right? One by one, right? The exam may first figure if you draw it like that, you can put a one and right also. First figure, right? In this position, in this position, normal reaction, normal reaction, capital R, normal reaction, capital R, normal reaction, capital R is acting vertically upward through the center of gravity. Is acting vertically upward through the center of gravity of the body, neutralizes neutralizes the weight of the body, neutralizes the weight of the body and keeps the objects in equilibrium. Keeps the objects in equilibrium. And also right there, here, here, the normal reaction act of the body is uniform. Normal reaction acted on the body is uniform. So all points the similar like forces acted and it's uniform. The resultant is this normal reaction acted on the body is uniform. Then write this even below this one, right? Right in here, here, system of uniform normal reaction. System of uniform normal reaction. Reaction. Sum of normal reactions. Normal reactions. The uniformity is broken. Reactions. The uniformity is broken. Uniformity or is broken. The right side from the center of gravity, it will be large, right? It will be large. Right side of the center of gravity as 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 its line of action is acting on as its line of action is acting through the center of gravity of the body. Through the center of gravity of the body. they still come towards this side. But this part now, not at the middle, R is not at the middle, R comes towards the right side. So then this side, the forces acting on this side is much greater than this one. When you take it out, what happens? Little bit, this side the forces increases, and at this point, the total force is acted on that point only. No forces acting on these two sides. Then you can consider this just touching this point only. Okay, then right there, the third case. In this position, and the third one right there. In this position, the object or body is touch. Is touch. The surface at the point body touches the surface at the point where the line of action of force and the normal line of action of the weight and the normal force action of the body and the action of the weight and the normal force. It's touched at the point where the weight line of action of the weight and the normal force is passed through. It's passed through. It's passed through. It passes in a point taking with the right action. It's passed through. It's passed through. And also it is passing through the edge of the table, and also it is passing through the edge of the table. So this is the limiting situation or limiting equilibrium position. Limiting equilibrium position. Right, last one. In this case, the weight of the body gives a torque. Weight of the body gives a torque about the edge of the table. About the edge of the table. On the edge of the table, and the body will rolls down, or body will topple at the edge. And topple due to the movement of the weight, right? Or torque of the weight. And it's a limiting case. So according to this, you can write for a uniform body, the maximum length which the object can take out from against the edge of the table, it is half of its length. Because until the center of gravity and the normal reaction acting on the same point, you can take it out. So whether you take out if due to the moment, because the moment should be zero when it is in equilibrium. But here the moment is not zero. So then it will not be in equilibrium. Yes, no rotation. The rotation equilibrium will be broken. Okay, you want to write that's the maximum length which object can take out from the edge of the table is the half of its length. Or you need to keep in mind that the limiting frictional or limiting equilibrium case, center of gravity would be at the edge of the table. Okay. You can put this line right there in this situation. And the limiting equilibrium case, center of gravity is at the edge of the table. Okay. We can say it's another situation like this, right? And the rest is right. Another case of this limiting friction, it's due to the friction also. The limiting equilibrium can make due to friction also. Let's say that's a body based on a center table like this. So plane. This plane, they just I will incline this angle. Let's say the angle alpha. To increase the inclination further. This is a rough surface, right? If there is no rough, you can not place like this because it will be slide down. In here, the weight of the body is acting on this mg, and then the component is mg cos the sine alpha. So this side is mg cos alpha. The normal reaction are on this. Also, you need to know something. This situation, the normal reaction acting on this, weight acting down, and the normal reaction from this side and this side, uniform normal reaction acting on all the points which are in contact. So the resultant is this R. But in here, when you raise this in, what's happening? The normal reaction, this point will be, this side must be smaller than this side. Side being smaller. Side getting larger normal force. The resultant will come somewhere here, let's say. Right. So at one point you can see can see that one point in this kind of situation you cannot. What is this situation? The normal force acting at this point, only this point only. Right? Only this so body will touch the surface only this point. Normal force acting at that point only. That means the normal force acting at this point will be zero. And all are in this way. Now, that is the limiting case in this mode. Here, this is the theta. After this point, here can be rolled. So, let's say this is the maximum angle which the body will not be sliding. So, this will be the sliding and this will be the rolling. The condition for rolling and sliding. If it is sliding, it's overtake the friction, right? The frictional force and this force, the component of the weight should be equal. So it is sliding. Until the theta, you increase the angle to theta. So here it is alpha. So it will slide. Further, you need to increase this without any sliding there. Further, you need to increase the inclination. There should be enough roughness. Roughness එක හොඳ තිබෙන්නේ නැත්නම් ඒ මුසන්න බෑ. ඒක උස්සලා තව ටිකක් උස්සගෙන ගියොත් එහෙනම් මොකද වෙන්නේ මේක? It's baby rolling. Here the less of sliding, and this is condition for rolling. So here the friction is applied. This case, this is also theta. Theta. So I will take this length. The radius of this cylindrical part is r, and this is half the height of the cylinder. So HO2 and HO2 is the height of the cylinder. So this is the condition for rolling. After this point, this will roll due to the weight of the moment given by this weight of the block. And this point is sliding. So in this case, that is the maximum friction which can obtain from this block and the surface equals to the component of the weight. එකක් මේක එහෙම weight component එකේ equal friction එක දෙක තමයි maximum. You can draw these one also as a second example. Right, for sliding, right, start sliding. This is also limiting case, right? Was sliding the sine alpha equals to the maximum friction. So the sine alpha you can write as mu r. R equals mg cos m. Understand it with mu. The alpha equals 10. This is a condition for slide. Two surfaces which slide when the angle increases, then this. And for rolling, you need to ensure that for rolling, that's a friction should be sufficient. Sufficient friction. Available. Height in weight and normal force. Be acted at the edge of the block. Should be at the edge of the block. So then directly you can write tan theta equals r divided by 2. Tan theta is equals to the r divided by h over. So will come up then 2r over h. Using this you can find the angle which the object is rolled down. 2r over h. So that's the way you can find condition for rolling a slide. So these two cases are limiting equilibrium cases, both cases. If the rotor roughness, the sufficient thickness or roughness is there, only this can be achieved. If not, it's rather sliding. So that is the limiting because if it starts sliding means it's break the equilibrium situation. Here also, if further you increase, it can roll down. Okay. Copy. Understand this clearly, right? Right. Okay, let's see some practical. Yes, then table, right? So to form blocks are placed at the edge as shown in this figure. So fine. What is the maximum distance x could be? Base is in equilibrium. That's the block. What is this maximum distance we can obtain for x? This is the length of a block is L. Right equation. There's two uniform identical blocks. Uniform identical blocks placed placed at the edge of the table as shown. Is at the edge of the table as shown. Length of the one rod is L. Length of the one rod is L. What is the maximum distance x? The maximum distance x. Mark x is there. X. Okay, there's two identical uniform rods of length L placed as shown in the figure. Right? Identical uniform rods of length L are placed as shown in the figure. Then write what is the maximum distance x? Maximum distance x which can achieve as the system is in equilibrium. As the system is in equilibrium. Okay, let's see now. How can do this? X we need to find, right? I'll take this length as A, length as B, then A plus B is the X, right? We know that for the equilibrium, limiting equilibrium of this upper block on this, that's the first block on the second block, this one on this can take maximum length out as its length, half of its length. So the center of gravity of the upper body be acted on this one, like this. So the center of gravity of the upper body. Then this A equals L over 2, half of the length of the upper. You can take out the body as the half of the length of this is can take out this maximum or the limiting equilibrium. And then the extra in here, center of gravity of this whole body, all the system. All the system means there are two blocks. It should be acted on the here. One, this is system. Total weight, that is empty here, and this is identical blocks. No, there's two empty. So then the center of gravity of the whole system should be acted on this. I'll draw this separately here, right? So understanding. This is, let's say, the A and this is B. So A. Center of gravity is there, individual center of gravity. Let's G1, G2, let's see. G2. Now the center of gravity of the system should be there, because center of gravity of this upper body should be acted on here, that is G2. Right. This is empty now, this is also empty. Now these two bodies, their center of gravity should be acted because same mass, right? This length is L over 2 from here to here. These two masses are equal. Then the center of gravity of these two, the center of gravity of the system should be acted on this place, that is 2 empty. Right. If this is L over 2, so this should be L over 4, and this also should be L over. This one is L over, that is the length A. This is the length B. So this is the edge of the table should be acted on this place. Keep in mind, keep it equilibrium. Edge of the table is there. So then you can say the B is also equals to the L over 4. So X equals then L over 2 plus L over 3 L over. At the maximum distance, you can take the blocks out. Is it clear or not? Hear me if I want to again explain. එරුණ නැත්තම් කියනවා ආයි කියන්න. Center of gravity එක H එකේ තියෙන්න ඕනේ. ඒ තියෙන විදිහට the system එක ඔයගොල්ලෝ center of gravity හොයන්න. ඒකට අර තියෙන දුරාටි හොයාගන්න. පුළුවන්. හරිද? තේරුණාද? net වෙනම එන්නේ. තේරුණානේ කියලා. යාගේ ඉවර නම් hand raise කරන්න. තේරුණ නැත්නම් ආයි කියන්න මම කියන්න. හරිද? දැන් ඉවරද? කියන්නේ දැන් ඉවරද කියන්නේත් නෑ කියන්නේත් නෑ another question I see right there. A cylinder of radius a cylinder of radius 2 meters and a height 8 meters. Cylinder of radius 2 meter and height 8 meter is placed on an incline plane as shown. This part of the question. If the coefficient of friction is 0.1, the coefficient of friction is 0.1. Coefficient limiting friction actually it is 0.1. At which value of theta, cylinder will slide down. Thus the cylinder start the slide. At which value of theta, the cylinder start the slide. The second part, if there is enough roughness, at which value of theta the cylinder start rolling out. At which value of theta cylinder start rolling down. This is what I quickly write. right? First case for sliding, you can say slide. So the weight of the body is mg here, say, and this side is mg. Let's say in this case, inside it is theta 1, that is for the sliding. It's the friction. So when you start sliding the side, there will be sine theta 1. So it's equals to F, that is mu r. So mg sine theta 1. It's mu limiting, right? That's mg cos theta 180. Normal reaction. Normal reaction is equals to mg cos theta, right? So then mg cancel out. So mu l, that's equals to tan theta 1. That's mu l is also 0.1. So the theta 1 is find. Tan inverse 0.1. That's 5 degrees and 42. And then it should be acted at this edge, because this edge is the normal reaction is also acting on this point. So this point, because it just to roll down, it means this surface is not touched with this, right? Then if touch it just only at this point. That's why normal reaction is also acting. So then this is radius and this is the height of the height. So this is, let's say, angle theta 2 here. This angle theta 2. Then tan theta 2 you can write. For rolling case, this r divided by h over 2. That is 2 r OH. 2 into r is 2 and h is 8. It's half. Theta 2 is 0, tan inverse 0.1. 26 degrees and 33. Okay. Can I erase this? It's not difficult one, right? You need to keep the mind. We start the, if it starts the sliding at this point, then you cannot achieve this one, right? So that's why I'm given you that there enough friction or enough roughness should be there. Slide when the right? I will erase this. I'll give another question. Um, right there, ladder, ladder has negligible mass and ladder has negligible mass and it rests on a frictionless floor and it rests on a frictionless floor as shown. The method ladder say as shown. The crossbar connects the two legs. Right? The crossbar connects the two legs of the ladder at the middle. Crossbar connects two legs of the ladder at the middle. The angle between the two legs, that means this is 60 degrees. Angle between the two legs is 60 degrees. A fat person sitting on the ladder person sitting on the ladder mass 80 kilogram. Mass 80 kilogram. Right. Right. Find the contact force exerted by the floor. Find the contact force exerted by the floor on each leg. On each leg. And the tension in the crossbar. Tension. Tension in the crossbar. Contact force means that's a frictional reaction as a result of that. It's better you need to draw the PVD diagram for this one and half and half. Then it is easy to take the moment for the equilibrium and this should be main equilibrium and okay. And then the resultant also should be equal to 0. Try to do it. It's not the difficult one. You can see here it is practical. Only you have seen this kind of letters. You do it, I will come at 1 minute. Okay, how you can do this? Just draw the free body diagrams of this all, and then this is smooth flow. So it's smooth frictionless flow. They pair. There's no friction. It's normal reaction. Only. And this point, let's say it's R, and it's R. This is in symmetry. So the same R you can use. It's for symmetry, right? So the tension weight of this man is 800. So how this weight will come? So the two both sides divided separate. I will draw the only one side there. So as a line diagram. So the R is 60 degree. So this is 30 degree now. And the force is acting on this man. It's half of the weight is acted the both sides. So we can consider 400 Newton, 80 kilogram. So 800 Newton, so 400 to this side. And the tension at this middle, say T. And also, this is a hinge system, right? To balance it, there should be any other horizontal force also. So that's a force acting at this point also. Yeah, this both side is equal and opposite, acting like this. That's how this side will be in equilibrium. We have to keep it is at the middle of the ladder, right? The length of the ladder is say L. And this L out to L out like this. You can show. This full system at the vertical equilibrium, that is 2R equals to the minus 800, that's equals to 0. So then R equals 400 Newton. The normal reaction at the flow, right? This is to taking the moments. Let's say this is the point A, made about it. Then this forces at this hinge is not come. The calculation. So here you know there is 30 degrees and this length is lower 2. So I need to get the distance between these two. That is a lower 2 cos. So then you can write the tension that's meant by this T into a lower 2 cos 30. And this will give the moment opposite way, right? Other side. 16. R minus R multiplied by L sine 30 equals to C. So the T you need to find. L cancel. It's half cos 30 is root 3 over 2 minus, let's see, R the other side, this part is cos to the other side, and R is 400, sine that is half again, half cancel. T equals then 800 or root 3. At the tension of the crossbar. Okay. Right. I will erase this, right? Then we start the work energy and power, right? It's questions we need to do, right? Because of more questions I will discuss. You go through the past paper question first, right? Because there are last year also, last year in 21, given a question related to the 2010 or 11 also there. And all the cases you need to consider is two you need to do. The direction, or any direction you can consider. That's a resultant force should equals to 0. There should not be any torque. So principle of moment you can use it. Clearly, work energy and power. Okay. Work, energy, and power. Discuss about work, energy, and power. First, we need to go. We discuss about the work. What is the work? Right, work done. Then come to the energy, and then last we can find power. Work, actually, the work means can define work like this. Normal general use. Any activity done by a person, we can call it a work. That's the any work, no? That is teaching, that's eating, the working, or everything now works, right? But in mechanics, if you want to do work, you need to apply a force. And also under that force, the point of application of the force should be moved, right? If it's not moving under that force, no work done by that force, you can say, right? If any force you applied on the body and the body is displaced due to that force, we can call that force is doing the work. The work, yes, when you're doing a work, what happens? If I pull or push on a body, the body displays, right? So then some work is done by me on that body. So that means the sum of energy from my body transfer to the other, right? So I think work done, we can say that work is the form of energy transit from one body to another body, right? The energy එකක body එකකින් නම් තව body එක transit වෙනකොට එක තියෙන විදිහට කියන්නේ this is called that's a work, right? The work cannot be stored as a in a body. It can convert it because that work means it's given a that by doing a work we can convert the one form of energy to another form of energy. That's the thing. Right. Without doing any work, you cannot change the energy or form of the energy of the body belongs. So that is important, right? Then the work is then the form of energy when it transit from one body to another body. And also in mathematically we can write that work is a product of force applied and the displacement under that force with the body used, right? Displacement into the force, that's we can write as a work done. The direction is important here because work done is since the work done is a scalar quantity, but the sign is very important. That's a sign for the work done. If negative work done, positive work done, or zero work done, we can say. If the negative work done means work done against the force applied. Positive work done means work done by the force applied. And the zero work done means the work done that we no work done actually, because the force, if the force is perpendicular to the direction of its motion, we can say that there are no work done by perpendicular forces, right? So that's why we can describe about the work. So should write the topic is work, energy, and power. Let's write the topic. Work, energy, and power. Okay, then write there. And the first write the subtopic as work, and then write work, and then write general use. General use. An activity general use, an activity by a person considered as a work. But in mechanics, the first force, unbalanced force should be applied to do work. Should be applied to do a work, and the point of application or point of action and a point of application of the force. Point of application of the force should be moved. Should be moved or should travel under that force. Under that force. Under that force. Right separately as a definition we can right. If a body gets displaced, if a body gets displaced, when an external unbalanced force acts on it, external unbalanced force acts on it, balance force acts on it, then that force is said to do work. Then that force is said to do work. Right. Uh, that right. By doing a work, an energy of an object, an energy by doing a work, an energy of an object is transferred into another object. It's transferred into another object. Therefore, therefore, the work is therefore the work is way of energy, form of energy. The work is the form of energy exist. Form of energy exists. When the energy of a body transfer, when energy of a body transfers to another body, through a mechanical force, to another body through a mechanical force. Okay, right. It's great, right? The amount of work done, the amount of work done is given by the product of the displacement of the right of amount of work done is given by the product of the displacement of the point of action of the body or action of the force. Amount of work done is given by product of displacement of the point of action, product of the displacement of the point of action of the force and the force acting in that direction. Force acting in that direction. Generally, we write this as a equation that force multiplied by the displacement. The same direction, right? If there's the force is not in the direction of the displacement, you need to consider the component of the force along the direction of the displacement. So that is important. If not, it's wrong, right? This work done. Write it as the equation, then work done is equals to the force multiplied by the displacement. General way we can write like this, but you need to keep in mind, I will give you write this, that's W. So write that is draw the figure and write that. First, you write this equation. Displacement is under the force acting on this. Same way, mass of the body, you can say it's same the work done equals to the force multiplied by the displacement. W means that's work done. Here was acting along the direction. Displacement. This is the displacement. Of point of action. Point of action of the force. You need to write it this way. If not, you got this wrong, right? If the point of application is not moves under the force acting. If it's move under the different force acting, we cannot say it's doing the work, right? That force do work because under that force, the point of application should be moved. So right. ඊළඟට වෙරණාද පුතා disconnect දාගත්තනේ කනම means this the W is the word, right? Okay, yeah, great. So if you finish, let me know, right? Okay, this is important. Then, if that was, you can see when you are bringing your traveling bag, so the thing you can bring it full current. Or better than force you apply in this way. Object is moving in this way. This kind of cases, the force and displacement not in the same direction. Right? Its component of the force will come towards the direction of the displacement. So the incline, if the force is applied in them inclination, the direction of the displacement, then we need to write this equation. We need to consider all that. Consider net force acting along the direction of the displacement, like this. You can write if the after this, right? If the force is acting at an inclination, force is acting at an inclination, force is acting at an inclination, the displacement, the displacement, then the work done is equal to the work done is equal to the product of the component of the force product of the component of the force in the direction of the displacement the component of the force in the direction of the displacement and the displacement and the displacement. Okay, this component of this force towards distraction at f cos theta, and the vertical component is f sin theta, but there's no motion for this direction. And this force should be applied on this body throughout the motion, right? මෙතෙන්දි විතරක් ඒ force එක දුන්නොත් it's doing the work on this place only. That's what we call the impulse. And we give the kinetic energy in that case. Just be putting up in a මොකක් හරි එකල කහලා කරනවා ඒක move වෙනවා. They will given a but in here that force should apply during this motion, right? මේ force එක මගදී අඩු වැඩි වෙන්න බෑ. Constant force is applied in this area. Right. So component is there. So then the work done you can write. You draw this and write the work done. That's a component of this direction, that is f cos theta multiplied by the displacement, that is fs, we call fs cos theta. This is a more general case. General equation is this one. We keep in mind this, not the previous one. Why? In the previous case, theta equals 0, this then equals to fs. Right. When you measure the distance, also displacement, you need to keep in mind that normally we consider the displacement from its center of gravity to center of gravity, right? That's how much the distance traveled by its center of gravity, center of mass. So this is a case, or that's the line of action of the force. The point of action of the force also you can consider. All right, it's writing. Let's try. And someone asked that what is the displacement here? Actually, displacement you need to consider that the displacement of the point of application or point of action of the force with respect to the frame which you are going to measure the or to calculate the work done. So that is all are relative things, right? So you need to consider it's also right there. Right, what is trying right there? This this equation, the S is this equation, that S is displacement of the point of action of the force displacement is, is the displacement of point of action of the force point of action of the force with respect to the or related to the with respect to the frame with respect to the frame which required to find the force which required to finding the force required to finding the work done, so not the force required to find the work done. And after that, right, the work done is a scalar quantity. Work done is a scalar quantity, and the SI unit of the work done, SI unit of the work done is joule. SI unit of the work done is joule, and its dimensional formula, that's ml square t minus 2. Its dimensional formula ml square t minus 2. Okay. Right after that, although work done is a scalar quantity, although the work done is a scalar quantity, so that is a scalar quantity, but its value may be positive, comma negative or zero, positive, negative or zero. Okay, then let's see how it's being positive, negative, and zero. So you can write it as a smaller subtopic. Work done in different situations. Work done in different situations. Done in different situations. Under that, the first one is the positive verb. Positive verb. Positive verb. Here we know that that's a pause. That's work done is equals to the response fs plus theta. So if theta is less than 90 degrees, the cos theta values are greater than 0 because cos theta greater than cos 90. Cos 90 is 0, so then its cos theta value is greater than 0. Because the cos theta function, you know, that is reduces with the theta, right? So if this is increases the theta, increases the cos theta decreases up to 0. So that means the cos theta values are greater than 0 up to 90 degrees, right? So then only we can say that W is positive. Here the case is then many practical situations. The force acted along the direction of the displacement. The angle is just within this range. That is 0 and 90. Between the 0 and 90. The cases we can consider displacement is in this direction, right? So we can say it's a positive work. Press right there. The work done by the force will be positive. Force done by the force. Force done. Work done by the force. Work done by the force will be positive for theta less than 90 degrees. Theta less than 90 degrees. You can write this. Theta less than 90 degrees, cos theta greater than 0 and W greater than 0. We can say that's the work done by the external force on the object. Externally, you're then forcing it and working the sides. To do the positive work, what happened actually? Energy of the body will increase. Okay, energy का value है positive work. Energy के नाम पर से आता है. Right there. ඒක එඩියා ගන්න positive work එකක් වෙන්නේ ඇත්තටම by the external force. Put the stand right there. When positive work done, when a positive work done, the energy of an object is increased. The of an object is increased. So that of an object is increased. As example, you can write here. In practice, there are numerous examples of positive work. There are numerous examples of positive work. Right? That's one example. When a body falls under gravity, work done by gravity is positive. Work done by gravity is positive. See how it's be positive. Work done, we can write it as cos theta. Here the body is fall under gravity. The gravitational force that is mg. That some writing is mg. The gravitational force is mg. Down. So its displacement is also in this direction. This ground. When it's fall down, it's going direction and the force acting in same direction. Because it's called free falling. In this case, the theta between the displacement and the force is 0. Right? That is 0. So then the cos 0 is equals to 1. The work done is F into S1. That is Ft into S. Ft I use as a gravitational force. So you can write as mgs also. This is positive. Positive. If any external force acted on the body and then is moved under that force, so all are positive. You can write this. It's a positive one. Displacement from here to here, it's a, when it is moving, you can say it's the work done equals mgs. Is the force, the gravitational force acting on the body. This gravitational force do the work positive. Right? Right. Then write the second one, negative work. negative work. Negative work means that when the angle is greater than 90 degrees, we can say that's a negative work. Right. Negative work done means actually the energy of the system reduces. So negative work done, that is when the direction, when the object is moves to this direction. You know that frictional force acted on the body is opposite friction. It's through the negative work. Right. So then the total work done you can consider as the negative work you need to reduce, and then the work done against the forces, then, not the work done by that forces. The friction is there, we cannot move the body, right? But the work done against the friction. You need to overcome the friction to move the body. So if there any external force, you need to apply it. So then that the work done by the friction you can reduces, and then the remaining the part of the force will do the resultant work done. Right. You can write under the negative work done. Then work done by a force will be negative. Work done by a force will be negative. Done by a force will be negative. For theta greater than 90 degrees. Right. So, right there, W equals F plus cos theta, that theta greater than 90 degrees, that cos theta less than 90 degrees. Because you know that it's after 90 degrees, cos graph goes to the negative side. That's why. The cos theta versus theta graph is 90 degrees. So it's goes to negative side. So it's negative where it's there. So therefore the W equals then W is less than 0. It's a negative. It's negative. Example, you can say when a body is thrown up, no forces acting on it now. So only the weight is acting. Weight acted down, but the object is moving in upward direction. The displacement you measured upward, right? Displacement as a vector, you can say displacement vector is upward. The force is acting down. In this work done, you consider, and the angle between these two, angle between the displacement and the weight, or that is theta equals 180 degrees. So 180. You finish this one, right there. When a body is thrown up, when a body is thrown up, work done by gravity, work done by gravity on the body is negative. Work done by gravity on the body is negative. Initially, the energy kinetic energy is not going to there's a potential energy increases, but the kinetic energy decreases. Work done by gravity on the body is negative. Negative. Right here, W equals F G S was 180. You can draw this diagram and then write this. Fg is mg here. Cos 180 is minus 1. This is minus mg. So it's negative. So later negative one. Another example you can write in, body moves in this direction. Let's say the body is moving. Due to the friction, we know that the body is moving under the friction. Friction is this, the displacement we curvature to this direction. This is friction, right? So the work done, you can write the angle between these two also 180. Yes, also 180. So it is minus F. Friction, you can write as mu r the minus mu r s. So you can say this as minus mu mgs. When the body is moving, it's under the friction. කරපු ටෝකන් අපි බයික් එකව තේ ටිකක් දුර ගිහලා නතර වෙනවා. එතකොට ඒ ෆෝස් එක නේ. ෆෝස් එක ඉනිෂියලි දුන්න තැනදී විතරනේ විතරයි. ඉම්පල්ස් එකක් නෙදෙන්නේ ඉස්සර. That's it. During the motion, it's moving under the friction. That's why it stops. Because that energy reduces. Energy reduces means actually it's energy converted to the non-mechanical energy. That's why it reduces it. Right? Is it okay? Then write third one. It's a zero work done. This. When you're doing the calculations, you need to use this kind of cases, right? And you need not forget to use the sign. It's negative sign. If you forget about the negative sign, you got wrong and wrong answers. Write the zero work. Done. If the theta is 90 degree, we can say it's a zero work, right? Directly right there. Right, the work done by force is zero. Work done by force is zero if either theta is 90 degree, either theta equals to 90 degree, or the displacement is zero. It's zero. Or the displacement is zero. We know that normal force is always that is acted perpendicular to the direction of its motion. And also the uniform circular motion, the centripetal force is acting always towards center. Circle like center. So that is always perpendicular to the direction of its motion. So those cases, work done by those forces is zero. Here you can write it that there is a theta then equals 0, so then the W equals 0. Here also, even any theta, if the display, if there is no displacement under the force, right? No displacement under the force, whatever the force acting or whatever the angle, so then work done is equal 0 because of the no displacement. If the case like this, if the body is moving, the displacement is measured to this direction. But the normal force acted, it's perpendicular, always perpendicular. So, the angle between the R and S is 0. S R is the force here. Is 0. Work done by R by normal reaction is equals to the R into S into cos 90. Cos 90. So this angle between this 0 90 degree, 0 90 cos 90 is 0. So that is done by the R, the normal reaction R, that's 0. So next example. Right, is the second example like that's work done by the centripetal force. That's work done by centripetal force in like uniform circular motion. Uniform circular motion. That also 0 work done. Object is moving around the circle. Body is there. Object moving. Displacement is in this way. And its centripetal force always acted towards the center of the circle. Like the angle between these two is always 90 degrees. So work done by the centripetal force, that's also 0 because of 0 and 90 degrees. Work done by the centripetal force is equal to yeah. Y Fc is the centripetal force. That is 0 always. There are no work done by the centripetal forces. This is 0 work done cases. And also we can consider the work done by friction. It's also be negative or positive or 0. Friction can also do some work. You know that when we do the friction, I told you that the friction can start the motion. So in that cases, we can say that the friction do the work on the body. But in normal general cases, we know that the friction is opposition force to the motion. So that is to do the negative. Friction applies in the body. Under the friction, if the body is not moving, that is in the case of the static friction, the body is not moving. So in that cases, we can say that the friction will not do any work. Okay, is it clear up to this point? It's about the work done. Need to keep this mind clear. within another one point when it's considered tell me another 1 point will stop after this. Let's see the vehicle. I will draw here. Also sector or the vehicle, right? The vehicle. And the forces acted on this vehicle, right? Say as if one is acted in this, and friction acted on, and two persons inside two persons inside they act forces reinforce the pull the let's say in this direction. This is F3 and this is F4, right? Think under this circumstances, body most distances. My forces degree. Yeah, I'm not going to draw that now. Persons, right? So, and other phrases is also there, right? They are game, we know. Apply the process. And the displacement here this is okay. Then you write this as a question. This is the same line as the same horizontal line. Right there. Find the work done by the forces. Find the work done by the forces F1, F2, F3, and F. So you need to find is all the work done by these all forces acted on this. Can they tell me? Quickly write and tell me the values and analysis of the class. Right. What are the work done by? Write the work done by F1. What is it? Yeah, no. What's F1? So F1 is acted on it. So under this force is moving to say this place. There is W1, let's say, which is F1 dot S. It's work done by F2. So it's a positive direction it's acted, right? It's minus F2 S. It's work done by 3. What is this? What is the work done by 3? Tell me one. So yeah, that's 0. Because here this F3 is applied opposite to the direction of its motion, but this internal forces acted on this body cannot move the body, this vehicle. So all they come with because of the external. දැන් වාහනයක එතකොට විත්තිය තල්ලු කරා කියලා වාහනේ යන්නේ නෑ. ඒ හින්දා මේ වගේ මේ forces acted, here the force is acted also, the point of application of the force is also moving, right? Look at this displacement. Even it's moving, but it's not move under the force acted at the F3, not move under this F3, so it's 0, and also F4 is 0. Similar. You need to keep that in mind. That's not enough. The force and also the displacement. You need to know that if that displacement is come under that force acted or not. If the force, there may be the displacement and the force, but if it is not come under that force, so you can say that no work done. Is it clear? Okay, next week we'll discuss about details regarding the work done and also the energy. But let's stop from this point today. Right? If you have any questions, you can ask them. Or you can send any questions to my enemy. You can write to me, call me, you can WhatsApp. No questions? No questions and no doubts? Then you can leave the place and take your participating. Okay, good night.